Okay. So as you know, we have already started the search algorithms, and search we have seen is ubiquitous. Every area of AI requires search. We saw this example of planning in the blocks world, which requires search, which block to pick, which block to stack, unstack, and so on. In computer vision, search is required when we do solve the correspondence problem. That is the left retina and the right retina. The points have to be put in correspondence. This requires search. Then in robot path planning, the robot has to take up, down, left, right movements and go from source to destination. This also involves search. In natural language processing, words have multiple meanings. Phrases have multiple meanings and interpretations. So arriving at the correct meaning is also a search problem. Then AI assistants, which help experts, also have to solve a search problem because the conditions in the input will satisfy many situations, and which operation to choose is also a search problem. So everywhere we need search. So that's why search is in the inner circle of the AI areas. Now we started getting into the nitty-gritties of search algorithms, the formulation of search algorithms. Everything begins with the description of state. This is the most fundamental point about search algorithms, and all the states form what is called the state space. Then operators transform one state to another. Start state is special, where the search operation begins. Goal state can be multiple, and the search terminates in the goal. Cost is the effort involved in using an operator, and optimal path is the least cost path, which is the final goal. So I mentioned that this is one problem we will implement in the lab, where there are 8 tiles which have to be placed in a particular order. Let's say 1, 2, 3, 4, 5, 6, 7, 8. And there is a blank space where the tiles move. So we have to go from the source state to the goal state by making these operations. Now, which operation to choose is the search question. And we are interested in finding the least cost path, the shortest path from the start state to the goal state. Now, I'm sure all of you have done a depth first, breadth first, and the extras algorithm for finding the shortest path. I'll show you that there is a general algorithm called general graph search, of which all these algorithms are particular instances under special conditions. So in this particular search problem, there are 4 operators, L, R, U, and D, and each has cost of C. Then we also saw this missionaries and cannibal problem. The missionaries and cannibals have to be transported to the right-hand side of the river from the left-hand side. And this is also a search problem because the boat can carry only 2 people at a time. And under no condition, we can have more cannibals than missionaries in any bank of the river. So then the search graph is constructed from the starting state 33L. Our goal is to go to 00R. Then another problem, which is this all the black tiles have to move to the right hand side of the white tiles, and there is a blank space here. The search is involved because a tile can jump over an adjacent tile to the empty block with a cost of 2, or a tile can slide to the adjacent empty block with a cost of 1. Okay, so this is also a search problem. Now, having seen all these instances of toy problems, of course, these are really toy problems. The actual search problems where AI help becomes essential are much more complex. The state space is much more difficult to decide. For example, diagnosing or interpreting a radiology plate, an X-ray plate where a patient's X-ray has been taken. There are many possible interpretations at every part of the X-ray plate. So how to arrive at the correct diagnosis is really a very, very complex search problem, and there the state space is not very clear. Similarly, predicting if there will be rain tomorrow based on today's conditions is also a prediction problem, and prediction often involves search. So none of these real life problems have such simple state spaces, but still we have to incorporate a kind of abstraction on the situation so that the search problem can be clearly defined. So let's go into the algorithmics of search. I intend to do today two pillars of artificial intelligence. One is the A star algorithm, the other is perceptron algorithm, from two sides of artificial intelligence. One is symbolic AI, the other is called connectionist AI, neural network based AI. So let's see, depending on the time permitting, let us do the algorithmics of search first. And for that, what is important to understand is what is called the general graph search algorithm, GGS algorithm. It's a very, very powerful framework of which all kinds of search are special cases. Okay, so here is an example of a graph, and let's see what it says. We'll spend a few minutes slowly looking at the graph. So there is a start state S, and from S we can go to three states A, B, and C, incurring costs of 1, 3, and 10 respectively. Going to C is the most expensive operation. Lesser cost is going to B, and least cost is A. Okay. Now, if we decide to take the least cost arc, let's say go to A. So this is a locally optimal strategy. It's a greedy strategy. At every step, go to the node which entails applying the least cost operator. But what is locally optimal need not be globally optimal. That's why we are looking for strategies which will ensure global optimality. So now look at this graph starting from S, G is the goal node. If you inspect the graph for a while, you will be very quickly able to tell me which is the least cost path. Okay. Is it SADG, or is it SBEG, or is it SCEG, and so on. So you can see that it is SADG, which is the least cost path. Its cost is 5 plus 1, 6 plus 3, 9, whereas other paths are 14 and 23. Okay, so SADG is the least cost path. We are interested in finding this path. Okay, so at any stage, I have no knowledge of what the least cost path is going to be. It has to be explored. So now let me give the algorithmics of these, and algorithms are always assisted by data structures, right? So for this particular problem, a data structure which is introduced is called two lists, an open list and a closed list. So open list are the nodes which are waiting to be expanded. Closed list contains the nodes which have been visited and do not need any more operation on them. Okay, so to illustrate this, let us see. The open list first contains the S node. We'll explain these 5 and 0 later. So S is in the open list. It is waiting to be expanded. Now S had three children, A, B, and C, as we have seen already, A, B, and C. So S gets expanded and goes to the closed list. A, B, and C get installed on the open list. Now we can explain the upper suffixes S1, S3, S10. What it means is that the parent of A is S, parent of B is S, parent of C is S. The other component in this tuple is the cost of the path, the least cost path found so far from S to A. Okay, let us remember this point always, that the immediate parent is recorded, and the least cost path from A back to S. Okay, the start node. That cost path is also recorded and maintained here in the upper suffix indices. So for A, the least cost path to S has cost of 1. For B, it is 3. For C, it is 10, as you can see from the graph by inspection, right? From A, the A to S is the path, B to S is the path, C to S is the path, and their costs are 10. Now let us see. Now, out of this A, B, and C, which one shall we expand? Okay, so that is the search question and the most critical question as far as the finding of the optimal cost path is concerned. This is the most critical question. If we pick up the right node always, then we'll be very guided in our search in terms of optimal path, and there will not be any useless expansion. On the other hand, if we pick up nodes which have no potential to give the optimal path, then there will be a lot of useless expansion. Breadth first search, depth first search, which are not informed of any domain knowledge, they are uninformed searches and they lead to a lot of useless expansion, as we'll see, and you will also verify this in the lab. Now, out of ABC, which one shall I choose? I do not have any additional knowledge to make the decision. Let me expand A. So when I expand A moves to the closed list. B and C are already there. Now A's child has to be now brought into the open list. As many children as A has, they have to come to the open list. Now A has only one child, D, and its our cost from A to D is 5. The cost of the path from S to D, the least cost path so far from S to D is 5 plus 1, 6. Let us see if all these are recorded. So B and C are there, D comes in, A has moved to the closed list. Okay, its job is done. And now D's immediate parent is A, and 6 means the cost of the best path so far from D to S has a cost of 6, which is indeed the case. Okay, this you see, D's path is from through A up to S. Okay, then we have B, C, D in the open list. Now, which one should I expand? Should I expand D? Then it will be like a depth first search, but no, let's see. Let's expand B. So when B is expanded, it comes to the closed list. Okay, and C is already there, D was already there. So B's child has to be brought into the open list. B's child is E. So yes, E. And we also have to record the path cost from E to S, which is 4 plus 3, 7. Yes, indeed, that is the case. Okay, now B is in the closed list. Now we have C, D, and E. Which one should I expand? Let's say I expand C. I bring C here. Now E, C's child is also E. C's child is also E. So now the question is there anything special which needs to be done? Yes. So E was already expanded through D. Through D. So no, not through D. Expanded through A. Okay. So D, E, E, E. It was already expanded through B. Yes, that is what is recorded in the fourth step. And now C comes in. So the question is, should the parent pointer of E be changed? Okay, then it will become C and the path through C. Is it necessary? Let us see. So if E is coming through C, then the path cost is 10 plus 6, 16, which is not right because we have a lesser cost path through B, 4 plus 3, 7. So no change to E's parent pointer and no change to the path cost from E to S. So C comes to the closed list. Now we have D and E. Which one should we expand? Let's say we expand D. So D now comes to the closed list. E is already there, and now come F and G. Why F and G? Because D's D's child is G. Okay, and D's child is also F. So D has two children, F and G. So both come to the open list F and G, and their parent pointers point to D, and the cost of the path from F to S through D is 8. G also comes to the open list. The cost of the path from G to S through D is 9. So in the closed list, we have S, A, B, C, D. In the open list, we have E, F, and G. Now you see the goal is there in the open list. Now, if I pick up goal and expand it, my algorithm stops. That is the definition of the termination of the algorithm. The algorithm stops as soon as the goal node is visited and sent to the closed node. So E, F, and G are already there. Now, if the algorithms had a scoring function whereby it was scoring all these nodes in the open list, and if G had the highest priority, then G will get expanded and the algorithm will terminate. But somehow this is not happening. The algorithm decides to expand E. So E comes to the closed list. E does not bring in any new node. Okay, E because E's child is G. So G is already there, and there is no reason to change the parent pointer of G. The least cost path is through D. Then now also, if G could have been expanded, then a useless expansion of F would have been avoided. But let's say the algorithm is not intelligent enough. So F gets expanded, comes here. F doesn't have any child. Now G is on the open list. Now G comes to the closed list and the algorithm terminates because the goal node has been found. Now, if we follow the parent pointer from G, we'll find the least cost path from S to G. Okay, not least cost, a path from S to G. So we see the parent pointer of G, which is D. We see the parent point, we look for the parent pointer of D. Where D is here. D's parent pointer did not change. D's parent pointer is A. And A's parent pointer is S. Okay, so G's path is from D to A to S. So D following the back pointer from G to D to A to S, we have found out the path. Okay, so you have seen how the algorithm works, and what you saw just now is essentially the breadth first search. Okay, at every level, we are expanding all the nodes at a particular level. So we first expand A, B, C, one after the other. We did not go to D before expanding B. Do not go to D before expanding C or E. After ABC is expanded, we can expand D and E. So finish that particular level. And then finally F and G. G comes last of all. So the useless expansions are B, C, E, F. Okay, these are useless expansions. Now, is the path the least cost path? Yes, indeed. The algorithm has found out the least cost path, GDAS. And this we have also have seen by inspection is the least cost path. The reason it has been able to find out the least cost path is that breadth first search is a special case of heuristic search where heuristic value H is 0. Okay, that's why it is guaranteed to give an optimal path. Breadth first search with uniform breadth first search with uniform cost, but sorry, non-uniform cost is a special case of Dijkstra's algorithm. Okay, so all these Dijkstra, BFS, DFS, these are special cases of this general graph search strategy, which is a very powerful framework. Okay, I hope you have understood the algorithm and how the whole algorithm is controlled by two data structures, the open list and closed list. They play a critical role in this algorithm. Okay, So this was general graph search. Let me give the formal statement of the general graph search algorithm. This is from a very classical book of artificial intelligence called Principles of AI by Niels J. Nielsen. Okay, this is an excellent book, especially for search and logic and planning. So the first step of the algorithm says create a search graph G consisting solely of the start node S. Put S on a list called open, which we have done. Create a list called close that is initially empty. Now loop, you'll have to come back here again and again. If open is empty, exit with failure. Okay, this is one of the termination conditions. If you have not found out the goal node and there is no node to be expanded in the open list, then it is a failure condition. Select the first node on open and remove from open and put on closed list. Call this node N. Okay, the first node in the open list has to be expanded. Okay, if N is the goal node, exit with the solution obtained by tracing a path along the pointers from N to S in the graph G. Okay, so you have to exit with the solution obtained by tracing a path along the pointers from N to S in G. Exactly as we did in the example graph a few minutes back. We traced the back pointers from G up to S. Then expand node N, generating the set M of its successors that are not ancestors of N. Install these memes of M as successors of N in G. Okay, so this step is saying quite a few things. Essentially, this means that get all the children of N and put them on open list. Okay, install these memes of S as successors of N in G, generating the set M of its successor that are not ancestors of N. Okay, so we will not expand. Will not bring any ancestor of the node N. Okay, that is kind of obvious because the graph is directed, but the algorithm tries to be precise in this matter that ancestors don't have to be brought in, only the children. Okay. Then the step number 7 is quite long. It has a number of sub-steps. Establish a pointer to N from those members of M that are not already in G, that is not already on either open or closed. Okay, so new nodes which are coming to the open list as a result of expansion of N will have N as their parent. Okay, so that is true. Add these members of M to open list. For each member of M that was already on open or closed, decide whether or not to redirect its pointer to N. This discussion we had, you remember in the example graph, E node came from B, it also came from G. Okay, the node E came from both B and C, sorry, B and C. But there was no reason to change the parent pointer of E if the path to S from C would have been less costly, then the parent pointer would have changed. Okay, so this is what is being specified in 7. Then the next step is more involved. For each member of M already on closed, decide for each of its descendants in G whether or not to redirect its pointer. So this operation is more expensive, and this more expensive operation can be made cheaper by introducing a very simple strategy called monotone restriction, which you're going to see going forward. Now, what is it saying? It is saying that if the child generated from N is found in the closed list S, that means that child was expanded before. Okay, so then n now has children, grandchildren, etc. So if m is now if now the closed list child's parent pointer has to be changed, that decision may also affect its grandchildren, the descendants of n. So if that is affecting the descendants, then their parent pointers also have to be changed. So I'd suggest that you spend little time looking at this particular problem. It is not very easy to find examples where the parent pointers of nodes in the closed list also have to be changed. So that example I'd like to give later. For the moment now, if any node has been generated before, check whether its parent pointer has to be changed because of the recent expansion, and the path cost will have to be changed. Now comes 8, which is a very, very important step. Reorder the list open using some strategy. Okay, so lots of things are concealed under this particular step. Okay, this is the heart of the intelligent search algorithm. And then go to loop. If we go to loop, what do we see? If open is empty, exit with failure, select the first node in open. That means amongst the nodes in the open list, you have already decided which one to expand. And that is the first node in the open list. And how does it become the first node? Because we'll have to reorder the open list. So reordering the open list means you have to have a scoring function for each of these nodes. And the value of that function will be used to sort the nodes in the open list to give it a order. And then you'll pick the first node. Okay, so this is the general graph search algorithm. I very strongly suggest you look at each and every step of the algorithm, because that is the heart of our discussion now going forward. Let's move ahead. This general graph search algorithm is really a general umbrella. If the open list is operated as a queue, okay, first in, first out, then we have breadth first search algorithm. If the open list is used as a stack, okay, then we have depth first search algorithm. Okay, this is last in, first out. And if the open list is accessed by using a function f, which is composed of g plus h, then it is called algorithm A. We'll come to algorithm A very quickly. But let's see that BFS and DFS indeed come from this open list and closed list as a general umbrella. So let's see, if I have expanded S, then A, B, and C have come into the open list. The strategy is first in, first out. Okay, so A, B, C has come. A has come first, B then, and then C. So A is expanded. D comes into the open list, but D will not get a chance because it is first in, first out. So now B will be expanded. E will come. E will also not get a chance because first in, first out. So C will be expanded after that. So only after all A, B, C are expanded, we can visit D and E. Okay, and D and E will have to be exhausted at that level, after which F and G will get a chance. So this is clearly the breadth first search strategy. If we operate the open list as a stack, last in, first out, then A, B, C have come. C has come last, so C will be expanded. When C is expanded, E will come. Okay. Last in, first out, E will now get a chance to be expanded before A and B. And then E will bring G. G will now get expanded, then the algorithm will terminate. In this case, we see that depth first search will very quickly get into the goal node without any lot of useless expansion. It is quite directed, but it will not give the optimal path. Okay, but breadth first search is guaranteed to give the optimal path. Okay, so now we come to this very interesting algorithm called algorithm A, where each of the nodes in the open list is associated a function f. Okay, so that function is a composition or addition of two functions g and h. What is g? G is the estimate. Uh, no, G is the uh, cost of the least cost path found so far from S to a node n. Okay, for any node n, we compute two values, G and H. G is the uh, cost of the path, least cost path found so far up to that node from S. Okay, so G is obtainable because this is the way the algorithm operates. Plus H. H is the complicated part. H is the estimate of the cost in going from the node N to the goal node G. Okay, so now why is it an estimate? Because we do not know the path from the node, let's say here N1. From N1 to G, we do not know the cost of the optimal path. We also do not know the least cost path from N. If we knew, then there is no search involved. Okay, for any node, if we know the least cost path to the goal, there is no search involved. G, it doesn't require any estimation. G is known by definition. G is the cost of the least cost path found so far. H is the estimate of the least cost path. Okay, so this has to be estimated. Now, H can be made to satisfy what is called monotone restriction. That makes the search more efficient, but that little later. So algorithm A is a function f is maintained with each node n such that fn equal to gn plus hn. N is the node in the open list. Node chosen for expansion is the one with least f value. For breadth first search, h is equal to 0. G is the number of edges in the path to S. Okay, where number of edges in the path to S. Okay, and for DFS, H is equal to 0 and G is equal to 1 by the number of edges in the path to S. 1 by the number of edges in the path to S. So you can see that with this formulation, giving expression for G and H, we can derive breadth first search and depth first search from algorithm A. Okay. Now comes the one of the most important pillars of AI, algorithm A star. So this is one of the most important advances in AI. GN is the least cost path from N to S found so far. HN is less than or equal to H star N, where H star N is the actual cost of the optimal path to G, node to be found from N. Okay, so algorithm A star is like A, except that it has one more constraint. H is indeed the estimate of the least cost path from N to the goal. Since the path is not known, H is also not known. But so H always has to be estimated. The additional constraint is that the estimate should be such that it is less than or equal to H star N, where H star is the actual cost of the optimal path from N to the goal node, actual cost. Now the question is, can you really come up with a heuristic H? H is called the heuristic, such that it satisfies this constraint of being less than or equal to H star N? The answer is yes, if we know the properties of the problem. Okay, and we can also see, which will be proved as a theorem, if H is less than or equal to H star, that is the actual least cost path's cost, then A star is guaranteed to give you the optimal path. You can also see that why breadth first search gives you the optimal path, because since for breadth first search, H is 0, H is 0, it is nothing, 0 is always less than the actual cost of the least cost path. So breadth first search gives you the optimal path. And optimism leads to optimality. This will help you remember the property of the A star. The heuristic has to be less than or equal to H star. Okay. So A star algorithm, the definition and properties are as follows. We'll come to this little later, but let us try to see if this constraint or requirement of H being less than or equal to H star, is it realistic? Okay, it is realistic, as we can see from from the 8 puzzle problem. Suppose in the 8 puzzle problem, the starting state is this 214 783 56. And the final goal is 1 2 3 4 5 6 7 8 with the blank space here where the tiles can move. Now n is an intermediate state 1 6 7 4 3 2 5 blank 8. We have come to this intermediate state from S by applying operators. H star n is the actual number of moves to transform n to G. Okay, so H star in n is the actual number of moves to transform n to G, the least number of moves. And H1n is the number of tiles displaced from their destined position. So here is the first heuristic proposed. So we are saying that the H value for a node n is such that the number of tiles displaced from their destined position is the H value. Okay, so this is the first heuristic. It is called displaced tile heuristic. Another heuristic is called Manhattan heuristic. This is H2n. This is the sum of the Manhattan distances of tiles from their destined position. So clearly both H1n and H2n are less than or equal to H star n. Let us see how it is so. So take this configuration 1 6 7 4 3 2 5 8. Now 1 is in the right position, 2 is not in the right position, 3 is not in the right position, 4 is in the right position, 5 is not, 6 is not, 7 is not, 8 is not. So displaced tile heuristic says that you will have to move these tiles which are displaced from their final position. At least you will have to move them. Okay, so the number of moves will be at least equal to the number of displaced tiles. We'll have to place them in the right position. Okay, so the heuristic value in this position for n will be equal to the number of displaced tiles, which is 2, 3, 5, 6, and 7. Okay, so 5 is the heuristic value. I need to make at least 5 moves to go from n to G. And this is definitely less than or equal to the actual number of moves required, least number of moves required to go from n to G. But you can have a more powerful heuristic, which is H2n. That powerful heuristic is exploiting the problem knowledge much better. It is saying the heuristic value will be equal to sum of Manhattan distances of tiles from their destined position. So the sum of Manhattan distances of 1 from its destined position is 0 because it is in the right position. For 2, 2 should have been in the central location of the first row, but it is in the rightmost location of the second row. So it needs one x movement, x-axis movement, and one y-axis movement. So for 2, it has to move a distance, at least a distance of 2. Okay, so similarly for 3, it is 2, 4, it is 0, for 5, it is 2, 6, it is 2, 7, it is 3, 4, 7, yeah, 7 it is 4. It has to move 2 y distances and then 2 x distances, 4. And for 8 it is 1. So this is this heuristic value is much more than the heuristic value h1, and also is closer to the actual distance that has to be covered for n to go to g. So it's a much better heuristic, much more aware of the problem property. And that's why we can say that this is a more informed heuristic. And the proof of pudding is in eating it. You will implement in the lab all these heuristics, the breadth first search, the depth first search, the heuristic H1, the heuristic H2. OK, all these we will implement and see that better heuristic gives rise to better performance in the sense that much less number of nodes will be expanded in discovering the optimal path. OK, so this will be the lab exercise next Thursday when you go to the lab. Implement the A-star algorithm. You simply have to maintain the values of G and H, and H value will be taking H, the 4 or 5 different heuristic values will be taken up. And then it will show you that more powerful heuristic indeed is better. OK, so we have started a very important discussion, namely the discussion on A-star, which is surely one of the most important algorithms of artificial intelligence. A-star algorithm gives rise to beam search. It is used in decoding. A-star-like algorithms mushroom with many different formats, many different variations. So this is indeed a foundation for AI. Implementing A-star will really give a lot of insight into how AI operates. I'll finish the class today with the request that all of you should form groups of 2 for doing your assignments in the lab and also your final project. Okay, and I'm sorry about the confusion today. The class is on Thursdays at 10:30. Okay, thank you. You can stop the recording. Harsh, you can come to the near the screen also.
Yes, sir.
So the slides are visible, right, in the screen?